Hi, Stu Schwartz, MasterMathMentor.com. This is video AB23. The topic is economic optimization, and it covers the AB manual pages 143 through 145. Suppose your parents decide to give you a graduation present of $25,000 to go and buy a good used car. You sit down with your parents and determine the make and model you wish to buy based upon safety ratings. You and your parents then work out the features you would like the car to have, some as safety features and others as convenience. You decide that you would want your car to have the following features: air conditioning, Bluetooth connectivity, a sunroof, a blind spot monitor, anti-lock brakes, a backup camera, and cruise control. Your parents have put aside $25,000 for the car, but may be willing to come up with slightly more money, although they will be reluctant to. You also realize that you might not be able to get all the features you want with that amount of money. There are several approaches that people usually take when making a decision of this nature. Approach 1 is to spend the $25,000 and get as many features as possible. In this case, we are maximizing the features given the constraint of spending no more than $25,000. Approach 2 is to find a car with all the features and spend as little as possible, even if it is over $25,000. We are minimizing the price, given the constraints of getting all the features. Approach 1 is usually taken by people buying houses. They have a wish list of house features, including location, size, bedrooms, bathrooms, garage, acreage, to name a few. And they also have a budget, knowing how much they can spend and knowing they cannot go over that figure. They know they will not get everything on their wish list, but try to get as many as possible. Approach 2 is usually taken by people who want a job done. For instance, homeowners are renovating a kitchen. They decide that they want stainless steel appliances, granite countertops, a tiled floor, and under-counter lighting. They bring in several contractors, explain what they want, and then accept bids. Typically, the job goes to the lowest bidder. So purchasing your graduation car is an optimization problem. Either you maximize the features on the car or minimize the price. Sadly, you can't have both. A lot of features and a cheap price. That's what this video deals with: economic optimization. Number 1 reads, a trucking company has determined that the cost per hour to operate a single truck is given by C of S equals 0.1 s squared minus 10s plus 450, where s is the speed that the truck travels. At what speed is the cost per hour a minimum? What is the hourly cost to operate the truck at that speed? Assuming that the truck can travel from 0 to 75 miles per hour, what is the range of hourly cost to operate the truck? The math in this problem is fairly simple. Since we want to minimize the cost per hour, we take that function and take its derivative, and we get 0.2s minus 10 and set it equal to 0. So therefore s is equal to 50 miles per hour. Since we're asked the hourly cost, we plug that back into the C function and we get $200. Since we know there is only one relative extrema, and that occurs at 50, in order to determine the range, we must take a look at the endpoints. So we look at C of 0 and we get 450, and C of 75 to get 262.50. That means that the lowest value of hourly cost is our $200, and the largest is at $450. Although not required, we verify our solution graphically. Note our relative and absolute minimum at S is equal to 50. Also note that we have the absolute maximum at S is equal to 0. S equals 0 means that the truck is not moving, yet the cost per hour is $450. That is because we are probably paying the driver just to sit there. It is important that trucks be in motion in order for the company to make money. Number 2 reads, a nursery wants to add a 1,000-square-foot rectangular area to its greenhouse to sell seedlings. For aesthetic reasons, the owner has decided to border the area on 3 sides by cedar siding at a cost of $10 per foot, as shown by the figure to the right, while the remaining side is to be a wall with a brick mosaic that costs $25 per foot. What should be the dimensions of the side so that the cost of the project will be minimized? And what is that cost? And we have a chart to complete. In the chart, we see width and length. Normally, the width in a rectangle is the shorter side and length is the longer side. We really don't know that here. So we will say here that the width represents where the mosaic will be, and the length will be the 2 sides where the cedar will be. So if the width is 10 and the length is 100, because the area has to be 1,000, that would make the cedar cost $2,100, while the mosaic cost would be $250, making the total cost equal to $23.50. If the width were 100 and the length were 10, then the cedar cost would be $1,200, while the mosaic cost would be $2,500, and the cost zooms up to $3,700. If we border on ridiculous and make the width equal to 1,000, making the length 1, then the cedar cost would be $10,020, while the mosaic cost would be $25,000, and the total cost would be $35,020. Now that you have an idea how to work with the numbers, let's work with variables. Let's call the width X and the length Y. So the cedar cost will simply be 10, quantity X plus 2Y, while the mosaic cost will be 25X, and the total cost will be 35X plus 20Y. So our cost is 35X plus 20Y. There are 2 variables, so we need to have a relationship between the variables, and our secondary equation will be xy is equal to 1,000, or y is equal to 1,000 over x. Replacing y, we get c equals 35x plus 20,000 over x. And we now take the derivative, and we get 0 equals 35 minus 20,000 over x squared. That gives 35x squared equals 20,000, and x is equal to 23.905. So we find that the width, which is where the mosaic will be 23.905 feet, while the length, which is where the cedar will be, is 41.833 feet. And the total cost of the project is $1,673.32. That is the minimum cost for building this rectangular area. We see the graphical confirmation and the minimum at the point 23.905 and 1673. It is clear that there is no maximum cost. We can make one of the sides as large as we want, and the other side will become very, very small. Therefore, either the mosaic or the cedar cost will be astronomical. Number 3 reads, a real estate company owns 100 apartments in Chicago. At $2,100 per month, each apartment can be rented. However, for each $75 increase in rent, there will be 2 additional vacancies. How much should the real estate company charge for rent to maximize its revenues? Complete the chart. Students who have never seen a problem of this nature frequently are at a loss of how to begin. The chart method really brings the problem into focus. We have several columns: $75 increases, rent, apartments rented, and revenue. Suppose we have no $75 increases. That means that the rent will be $2,100 and they will rent all 100 apartments, making the revenue $210,000. When we have one $75 increase, the rent goes up by $75 and we're up to $2,175, but they only rent 98 apartments. Still, the revenue is higher, $213,150. If we have two $75 increases, now our rent is up to $2,250, but we only rent 96 apartments, and yet our revenue is still higher, $216,000. So it seems that as we increase the number of $75 increases, that the total revenue becomes greater. However, when we get to 50 $75 increases, the rent is a whopping $5,850, but there are no apartments rented, and therefore the revenue is zero. So if the revenue has gone up, but now is back down to zero, clearly there must be a maximum. So we will say we will have X $75 increases, making the rent $2,100 plus 75X, and making the apartments rented 100 minus 2X. So the revenue is their product, 2,100 plus 75X times 100 minus 2X. So the solution is now fairly easy. The revenue is the product, 2,100 plus 75X times 100 minus 2X. Expanding that, we get 210,000 plus 3,300X minus 150X squared. We take the derivative and set that equal to 0, and therefore 0 equals 3,300 minus 300X, and X is equal to 11. That means that the rent will be 2,100 plus 75 times X, and it goes up to 2,925, meaning that the number of apartments rented will be 100 minus 2 times 11, or 78. And therefore the monthly maximum revenue is $228,150. We see the graphic confirmation. Realize, though, that by maximizing our monthly revenue, we have 22 vacant apartments. The company actually makes more money not renting apartments than renting them. That may not be the best strategy, though. People do not like living in buildings with vacant apartments. It makes them feel unsafe. So there is more into determining the rent price than just monthly maximum revenue. Finding the optimum price for a product to maximize revenue is an age-old problem. Charge too little and you will sell many of your product but not make much money. charge too much and you will make a great deal of money on each one you sell, but you won't sell many. The concept of a sale is to lower the price in the hope you would sell more than you usually would and make up the difference in lost revenue due to the lowering of the price. Calculus is terrific in determining what we should charge in order to maximize our revenue. But it is dependent upon equations, and rarely do we get equations in real life. Typically, finding the best price is a matter of trial and error. A closed box with a square base is to have a volume of 1,800 cubic inches. The material for the top and bottom of the box, which is the shaded section in the figure, costs 30 cents per square inch, while the material for the sides costs 10 cents per square inch. We want to find the minimum cost of the box. The figure is as shown. The base, both top and bottom, have sides of x, while the height will be y. We will not generate a chart for this problem as it is too time consuming. By now we should be able to write our equations. The area of the top and bottom are each x squared, and the area of the sides are each xy. So our cost is 0.3 times 2x squared plus 0.1 times 4xy. We have two variables, so we need to have a relationship between them. And since the volume has to be 1800, we say x squared y is equal to 1800. It is easier to solve for y, so y is equal to 1800 over x squared. So our cost is 0.6x squared plus 0.4x times 100 over x squared. From there we can take the derivative and get 1.2x minus 720 over x squared is equal to 0, getting 1.2x cubed is equal to 720, and therefore x is the cube root of 600. Therefore our base is 8.434 inches, and our height will be 1800 over 8.434 squared, or 25.303 inches. Therefore, the minimum cost is $128.05. The graph not only confirms the answer, but also shows the logic. If we had a very small base, with x being a small number, yes, the material for the top and bottom would be small, but the height would therefore be large, and since we have 4 sides, the cost would be very, very large. Similarly, if our x was large, then we would have a lot of the money being involved for the two bases. The sides would not cost that much, but the bases would also be astronomical. A small television company estimates that the cost in dollars of producing X units of a new model TV is given by C of X equals 80,000 plus 40X plus 0.2X squared. Find a production level that minimizes the average cost per unit. Complete the chart and explain why the average cost to produce TVs is so great for either small or large numbers of units. For 10 units, it costs $80,420 to produce them. Therefore, the average cost is $8,420. If they made 100 units, it would cost $86,000 to produce them, and therefore the average cost goes down to $860. 1,000 units has an average cost of $320. However, 2,000 units, the average cost goes back up to $480. And at 5,000 units, the average cost goes up to $1,056. The cost of producing X units is 80,000 plus 40X plus 0.2X squared, so the average cost is that expression divided by X. We divide each term by X, and we get 80,000 over X plus 40 plus 0.2X. Taking the derivative and setting it equal to 0, we get 0 equals negative 80,000 over X squared plus 0.2. Therefore, we get 0.2x squared equals 80,000, or x is equal to the square root of 400,000. Therefore, x is equal to 632.46 units, making the average cost $293. So therefore, when we make 632.46 TVs, the average cost for producing those TVs is at a minimum. The graph confirms the result and also illustrates that if they produce a very small number of TVs or a very large number of TVs, the average cost is huge. Why? When X is 0, meaning they make no TVs, the cost would be $80,000. The reason for that is that there are startup costs. You need a building, you need machinery, you need to heat the building. So even if they make no TVs, they're out a lot of money. From there, the average costs go down. But realize that there are a lot of machines necessary to make a TV. As we say, to make a small number of TVs would be very expensive due to the cost of all these machines. But to make a large number of TVs might involve hiring more people or buying more machinery. There is a sweet spot for the optimum number of TVs to create. That is 632 TVs. Number 6 reads, a TV cable is to be laid from the cable company to an island 7 miles offshore at a cost of $20,000 per mile along the shoreline and $50,000 per mile underwater. How should the cable be laid at the least expensive cost if the distance along the shoreline is 12 miles as shown in the figure to the right? What is that cost? Also, what is the most expensive way to lay the cable? We want to complete the chart to help us see the relationship. As we see in the diagram, we will let x represent the distance from the perpendicular line from the island to the shoreline. And we will examine 3 possibilities for x, 0, 6, and 12. Let's start with x is 0. When x is 0, the water cost will be the 7 miles times 50,000, or 350,000, and the land cost will be 12 times 20,000, or 240,000. So it will cost $590,000 to lay the cable in this way. Now let's look at x is equal to 12. If x is 12, then we're going directly from the island to the cable company. So therefore, the water cost is the distance, which is the square root of 7 squared plus 12 squared, which is the square root of 193 times 50,000, or $694,622. There is no land cost, so that is the total cost of the project. Now let's lay it halfway when x is 6. So when x is 6, the water cost will be the distance, which will be the square root of 7 squared plus 6 squared, or the square root of 85, times 50,000, or $460,977. And the land cost will be 20,000 times 6, or 120,000. And therefore our total cost is $580,977. So far, that is the best figure, but maybe we can do better. So our cost equation is 5 square root of x squared plus 49 plus 2 quantity 12 minus x. We use 5 and 2 rather than 50,000 and 20,000 to make things easier. At the end, we will calculate our cost by multiplying by 10,000. So therefore, our derivative, we get 0 is equal to 5x over the square root of x squared plus 49 minus 2. When we cross multiply, we get 5x equals 2 square root of x squared plus 49, or 25x squared equals 4x squared plus 196. 21x squared is equal to 196, and therefore x is equal to 3.055 miles. So when we calculate the minimum cost, we get $560,789. Since there is only one critical value, the maximum cost must occur at one of the endpoints, and we've already done that work. So we find that the maximum cost is $694,622, and that is if we construct our cable completely underground. The graph confirms the solution. Note, however, that there is not a big discrepancy between the minimum cost at $561,000 and the cost if we lay the cable directly to land, which would cost $590,000. Most people know that if you lay a cable underwater and something goes wrong with it, then it's much harder to service. So it may be that even though it might cost a little bit more, you may want to have the shortest distance of cable underwater. 7 reads, a rectangular area is to be fenced in using 2 types of fencing. The front and back uses fencing costing $5 a foot, while the sides use fencing costing $4 a foot. There are 2 parts to this problem. Part A asks if the area of the rectangle must contain 500 square feet, what should the dimensions of the rectangle be in order to keep the cost a minimum? Question B asks if the builder has only $800 to spend, what is the largest area that can be fenced in? This problem describes the same situation as our introduction when you were faced with getting the most features on your car for $25,000 or for getting all the features on the car for the cheapest price. In Part A, we must have 500 square feet, and we want to do the project in the least expensive way. Whereas in Part B, there is a fixed amount of money allocated for the project, and you want to get the biggest bang for your buck. For both questions, we will use the simple diagram of a rectangle with opposite sides x and the other pair of opposite sides y. In Part A, the cost will be 5 times 2x plus 4 times 2y, which is 10x plus 8y. There are 2 variables, so we need a relationship between x and y, and we know that x times y must equal 500, or y is equal to 500 over x. So therefore the cost is 10x plus 4,000 over x, and taking the derivative we get 0 equals 10 minus 4,000 over x squared, or 10x squared is equal to 4,000 and x is equal to 20. So the front and back must be 20 feet, making the sides 25 feet. And therefore the cost of our rectangular area would be $400. The graph confirms the answer and also illustrates that there is no maximum cost. By making one of the sides very, very large, you can make this project cost as much as you want it to. In part B, the expression to be maximized is A equals xy. Two variables again, so we need a relationship between x and y, and we know that the cost, 10x plus 8y, must equal to 800. And therefore y is equal to 100 minus 5 fourths x. Therefore a is equal to x times 100 minus 5 fourths x. Taking the derivative and setting it equal to 0, we get 0 equals 100 minus 5 halves x, and that gives x is equal to 40. So now the front and the back will be 40 feet, making the two sides 50 feet. And that will give us a maximum area of 2,000 square feet. The graph also confirms the fact that the largest area we could build is 2,000 square feet. It also shows that there is no real minimum. We can get as close to 0 as we like by building very, very long and narrow rectangles. So far, the primary and secondary equations have been fairly straightforward to generate. Let's look at a problem that's a bit more challenging. Number 8. The cost of fuel to propel a ferry boat through the water in dollars per hour is given by f of v equals v cubed over 8, where v is the speed of the boat in miles per hour. In addition, the cost of labor and maintenance to run the ferry is $2,000 per hour. At what speed should the ferry travel to minimize the cost per mile traveled? This is a problem where units are very important. We talk about the cost to run the ferry in dollars per hour, which will be the cost of fuel plus the maintenance cost. And that will be f of v plus 2,000, or v cubed over 8 plus 2,000 measured in dollars per hour. Now look at the question that was asked. We want to minimize the cost per mile. That would be in dollars per mile, not dollars per hour. So our expression must be in terms of dollars per mile. How do we change dollars per hour to dollars per mile? We multiply by hours over mile, which is the same thing as dividing by v miles per hour. So our m of v will be v cubed over 8 plus 2,000 divided by v miles per hour, dollars per hour. And that turns out to be v squared over 8 plus 2,000 over v, dollars per hour times hours per mile, and the hours cancel out, and we have the correct expression in terms of dollars per mile. Now it's easy. Take the derivative, set equal to 0. So 0 equals v over 4 minus 2,000 over v squared. 2,000 over v squared equals v over 4, and v cubed equals 8,000, meaning that v is equal to 20 miles per hour. We verify our answer graphically, and it makes sense. If we travel much slower than 20 miles an hour, we will not pay that much in fuel, but it will take the ferry much longer to reach its destination, and for every hour you're paying $2,000 for maintenance. If you travel much faster than 20 miles per hour, you will not be paying that much for maintenance, but you will be paying a lot for fuel. So it makes sense that the answer in terms of speed is not too high and not too low. There are a number of interesting homework problems, and I recommend you try some. The AP exam does not stress optimization problems. However, it is important for students to see how real-world situations can be solved with calculus. Some of you will take a course in college in multivariable calculus, where we try and optimize a solution based on several variables, not just one.